Good morning, sir.
इससे पहले you were having any class?
Mathematics.
Okay. You were joining late इसलिए थोड़ा सा कोई सेकेंड क्लास टेस्ट होना है आपका? We planned that there will be two class tests throughout the semester, and first I took in the from before your mid semester, है ना? If I remember correctly. तो another was planned कि final exam से पहले एक आपका class test हो जाए, so that best of the two or average of the two, है ना? Average of two, दोनों में से या तो एवरेज लेंगे दोनों का या फिर बेस्ट ऑफ, दैट कैन बी कंसिडर्ड. अबाउट सुपर कंडक्टिविटी बिफोर दिस, है ना? इससे पहले कभी यू हैव नॉट, यू डू नॉट नो व्हाट इज सुपर कंडक्टिविटी, और यू हैव आइडिया अबाउट सुपर कंडक्टिविटी. Okay, you do not have any idea about superconductivity. So we'll be covering this unit in a will be contents which we'll be covering during this unit are, we'll discuss how superconductivity was discovered. It is a low temperature phenomena, and we'll see that this man on my screen, he's Camerling Owens, and he's father of low temperature physics, and he discovered superconductivity. And at low temperature, we'll discuss all the details how he discovered this new phenomena. Then we'll also discuss characteristics of superconducting material, what we mean by a superconducting material, and what are its properties or characteristics when it goes to this superconducting state. Then we categorize superconductors into two classes, like we say that they are low temperature superconductors and high temperature superconductors. As superconductivity is a low temperature phenomena, so we say that some materials, they become superconductor at very low temperature, so we categorize them under low temperature superconductors. And then with new discoveries, then people started making superconductors which can withstand high temperatures as well. So we'll discuss about them. Then the next part will be, we'll be talking about effect of magnetic field on superconductors. This is very important part. और यहाँ से application निकल के आता है superconductivity का. Okay, so what is how superconductor behaves when magnetic field is applied on a superconductor, or what is the effect of magnetic field on superconductivity of superconductors? This was studied by Meissner, and he talked about another property of superconductor, perfect diamagnetic property. So you should be aware of some magnetic properties as well. You should know what is diamagnetic material and what we mean by perfect diamagnetic material. Okay, or if you do not know, we'll discuss when we will do this. That is Meissner's effect. Then we have types of superconductors, type 1 and type 2 superconductors. So on the basis of their response to the magnetic field, we again categorize superconductors into two different classes, that is type 1 and type 2 superconductor, based on their response to the magnetic field. Then till now it was about only what are superconductors, what are properties of these superconductors, what are type 1 superconductors, type 2 superconductors, and other things. Then nobody, abhi tak kisi ne bhi, nobody explained what is super or why this phenomena is there. What is the reason for materials showing this property of superconductivity? So that was explained. First attempt was done by three scientists together. They were that theory was called BCS theory. It was done by Bardeen, Cooper, and Sheffer. These were three people who tried. First time they tried to explain what is the reason for superconductivity. So we'll see what was the reason or what they proposed or what they said. Then they talked about interaction of lattice with charge carriers or with in terms when we talk in terms of superconductivity, we talk about Cooper
Slide
pairs.
chain theory.
Yes,
The slide chain theory.
स्लाइड चेंज ही नहीं कर रहे हैं, अभी सिर्फ आपको ये बता रहे हैं कि हम क्या डिस्कस करेंगे इस पूरे चैप्टर में. आई एम नॉट चेंजिंग माय स्लाइड्स, है ना?
Okay, sir.
Okay. So this is first slide. You can see now. I'll shift to this presentation. It is about discovery of superconductivity. Camerling Owens, uh, also called father of low temperature physics, he discovered superconductivity. First time he observed that this material can be made superconductor, and we'll see how this happened. And superconductivity means when resistance goes to zero, resistance of the material goes to zero, then material is said to be in superconducting state. So we'll see exactly what this state is. But before that, let us start with the basics of conductors or resistivity, how it goes to zero, or what we mean by resistivity at ordinary temperatures or ordinary conductors. So you all know, this is what you know already, what you have done earlier in your lower classes. We have Ohm's law. According to this Ohm's law, we say that voltage applied is directly proportional to current, or we say that current through any conductor is directly proportional to voltage applied. So current flows through any conductor or any material. It depends on what is the voltage applied, and it also factor. There is another factor, that is the resistance of the material, that controls current flowing through the material. So we have a temptation that by applying more and more potential difference or voltage, we can run more current through the conductor. But at the same time, there is another phenomena, that is, or there is another thing, that is Joule's law of heating, or there is Joule's law, Joule heating. And this is what, with the flow of current through the conductor, there is this power, or that is energy is dissipated in the form of heat, that is I square R, or if it is total energy, then I square RT. So again, resistance is responsible for this Joule heating, and resistance for any material is what it is in terms of the intrinsic property, because resistance it depends on dimensions, it is length and area, but it is resistivity is the intrinsic property, and resistance in terms of this resistivity, or you can say this is rho times n over a. So resistance is important, resistivity is important. So we can say that the intrinsic property of the material, that is important to decide how material, or how it allows current to flow through it. It allows more current or less current, and at the same time we have to keep both the things in our mind, that Joule's heating will be there. So more current means what? More heating will be produced. So we have to optimize the things, and then we have to see how much current can be allowed to flow through any given material. If resistivity is less, then energy crisis को हम लोग कुछ हद तक solve कर सकते हैं. So we have these materials which are good conductors. They show, or they have very less resistivity. So we are looking for materials which have less resistance, so that we can minimize both the things. We apply less voltage to have more current, and less heating is produced, Joule heating is produced. So to have more current, we talk about what? We talk about low resistivity. So You can see here, these are the materials, best material having the lowest resistivity is silver. It is 1.55 is the resistivity ohm centimeter, and order is 10 raised to the power minus 6. Then we have copper next, second best conductor. Then gold, aluminium, graphene is also there. Graphene, but as it is what it is. It is वेरी लो. जब हम बात करेंगे कि लो डायमेंशंस की बात करेंगे, then we can talk about this graphene. If you understand, it is carbon, but it is single atom thick layer of carbon. Okay, that is what that is graphene. So we have not written it because it depends on number of factors, so I can write exactly what is the resistivity for this. Teflon having resistivity very high, and that is 10 raised to the power 25 ohm centimeter, just to compare what is the comparison. So what determines resistivity in metals? Resistivity for any material is positive, it is greater than zero, and resistivity is consequence of second law of thermodynamics, because with temperature we say randomness, freeness increases. So in a material we have freeness, more freeness with increase in temperature, and more freeness means what that there will be more resistivity, more collisions, so resistivity is what it is more. So we can, if we can find a material which has resistivity less than zero, or you can say equal to zero, so we can solve our energy crisis. So no dissipation of energy, and no voltage or continuous voltage will be required for flow of current through any conductor. So we understand that resistance or resistivity, it varies with temperature. There is temperature dependence. So we know resistivity, how it depends on temperature. This relation you have done earlier also. This is rho T, resistivity at any temperature T. And this is resistivity at some standard temperature, lower temperature, some standard temperature, 1 plus alpha. This is temperature coefficient of resistivity, means change in resistivity for unit change in temperature. And this is T minus T naught. This is temperature at which we are interested in finding resistivity, and T naught is the temperature at which resistivity is rho naught, that is the standard. So simply we want to make a statement here that resistivity is function of temperature. It varies with temperature. We increase temperature, freeness, randomness, entropy increases, and that increases resistivity of the material. So there is resistivity and temperature. So what we know now is resistivity. Now you can see here resistivity. Okay, resistivity is function of temperature. How minimizing resistivity. So factors resist. So it depends on temperature. Also depends on not. So that means pure crystal of any good conductor, it will be having lesser resistivity than impure crystal. So impurities, they lead to increase in resistivity. And this slope, you can see this is resistivity versus temperature graph. So this is how it is varying with temperature. And slope is always positive, means what? That resistivity always increases with increase in temperature. Okay, and conversely, It means that with decrease in temperature, resistivity will decrease. So with this, there are different theories about resistivity which were developed earlier in 19th and 18th century. There were three famous theories about resistivity. First was given by Calvin. You can see in this temperature, resistivity versus temperature. Calvin predicted that resistivity goes to infinity. It increases with decrease in temperature. As we are going lower and lower towards low temperature, this is increasing. Resistivity increases. So he said that electrons will be frozen, means with decrease in temperature, movement of electrons will be restricted or they will be frozen. They will not move at all, and the resistivity will go to infinity. This was the idea given by Calvin. It was given in 1902. Then another scientist, Dewar, he said that the lattice will be frozen. The electrons will not be scattered. As we know that resistivity is what it is due to lattice vibrations, and when electrons they get scattered due to these lattice vibrations, and these lattice vibrations they depend on temperature, randomness, entropy, as I said, second law of thermodynamics. With increase in temperature, randomness will increase or lattice vibrations will be more. So there will be more collisions, more scattering of electrons due to these phonons produced in the lattice. Phonons are this quanta of vibrational energy, like quanta of EM energy is what it is, photon. So quanta of vibrational energy is phonon. So we talk in terms of phonon. So it is what it is whenever there are phonon vibrations are there or lattice vibrations are there due to these phonons which are produced, means more lattice vibrations, okay, and more scattering of electrons. So according to Dewar, he said that this will be frozen, that lattice will be frozen, and electrons will not be scattered. They will move undeflected or without any scattering. So resistivity will decrease till zero. So this is what is predicted by Dewar. It goes to zero with decrease in temperature. Then there was another scientist, Mathinson. He said that residual resistivity will be there because of contamination and lattice defects. As we discussed earlier also, that there will be some residual. This is what it will not decrease to zero. With decrease in temperature, if even if we go to zero temperature, some resistivity will remain in the material, and this is due to because we cannot make materials perfectly pure, or you can say 100% pure. Some defects will be there, some minute impurities will be there, and due to those small defects and small impurities, it will be having some resistivity, residual resistivity will be there in the material. So these were different theories before discovery of superconductivity. ठीक है तो these are the main theories. And in the beginning of 20th century, what happened? ये सारा 20th century के beginning में there was a challenge how to reach zero Kelvin temperature or how to achieve low temperatures. And there was this scientist Dewar, he succeeded in liquefying hydrogen atom. And he liquefied hydrogen atom or hydrogen gas, sorry, he liquefied hydrogen gas and having boiling point 20.28 Kelvin, means when it will be in liquid state, its temperature will be less than 20.28 and it will boil at this temperature, that is 20.28, and above this temperature it will be in gaseous state. So he liquefied hydrogen by applying pressure and temperature condition by lowering temperature. If we lower temperature, ठीक है, तो क्या होगा, गैसियस स्टेट में जो मटेरियल होगा वो कंडेंस होगा, और प्रेशर भी लगाएंगे तो और कंडेंस करेंगे, तो वी कैन लिक्विफाई इट. Okay, and if we again increase temperature, then it will go from this liquid state to again vapor state. So, but in liquid state, it will be having temperature less than 20.28 Kelvin. So that means close to 0 Kelvin. This temperature is very small temperature. You all understand what is 0 Kelvin. Okay, don't get confused with 0 degree centigrade. It is 0 Kelvin minus 273 degree centigrade. Okay, so hydrogen gas gets liquefied. So this liquid hydrogen gas or liquid hydrogen, not gas, liquid hydrogen can be used to achieve temperatures close to zero. It is 20.28. But we want temperatures lower than this, and this gives you idea what is absolute zero, what we mean by absolute zero. We know that average kinetic energy of gas particles, it depends on or is directly proportional to temperature. More is the temperature means more is the average kinetic energy of particles. If we keep on decreasing temperature becomes lesser and lesser, so their movement will also be lesser and lesser, kinetic energy will be lesser and lesser until they stop at 0 Kelvin. So that is the absolute when there is no kinetic energy in the system. Now, this Camerling Owens, when uh, he said he asked himself a question that if we make material highly pure, because resistivity, it was known that resistivity is function of temperature and purity. By increasing purity, resistivity can be decreased. By decreasing temperature, resistivity can be decreased. He said that if I do both the things, so he asked himself a question: ki what would happen? Kya hoga if I make a crystal very pure and make its temperature zero, or I cool it down to absolute zero? So, what would happen to resistivity? What will be the resistivity of that material? Okay, so there were different theories, as I said earlier, that Calvin said that resistivity will go to infinity. Dewar said that it will go to zero at 0 Kelvin, and Matheson said that there will be some residual, and he's taking care of that residual resistivity by decreasing or by increasing purity of the material. So he attempted one experiment. उससे भी पहले let us see timeline कैसे develop हुआ वो experiment. But this is what is the origin of superconductivity. When this question came to his mind, he started thinking how we can achieve these low temperatures and what material should be used to see what happens to the resistivity, because we require a material which can be made highly pure. We want material जिसकी purity को हम high कर सकते हैं. So looking for such material. So he observed that for non-superconducting materials, then their resistivity does not go to zero when temperature is low temperatures are achieved or very low temperatures are achieved. But for some materials, he observed for some materials that this happens, that resistivity goes to zero. This is resistivity and it is going to abrupt change. Resistivity can be observed here, and the resistivity goes to zero at some particular temperature. So this is transition, that material, it goes from normal state. It is normal state. Normal state means when resistivity varies, or it is having some finite value, and it is having other characteristics material, and it goes to new state. It is superconducting state having different characteristics. We'll talk about that in more detail. This is how this happened, how superconductivity was discovered. This was first time superconductivity was observed by anyone. So this is the timeline how this developed. Uh, it started with discovery of helium on Earth. Okay, helium gas Earth पे exist करता है. Helium is there. It was not known till 1895. And William Ramsay in 1895, he discovered new gas, that is helium on Earth. And then after 13 years of time, in 1908, Camerling Owens succeeded in liquefying this gas, that is helium gas. Earlier we talked about liquefaction of hydrogen gas. Now he succeeded in liquefying helium gas, and and helium gas under temperature and given temperature and pressure condition, it liquefies and its boiling point is 4.22 Kelvin. Means in liquid state, temperature of helium is as low as 4.2 Kelvin. So we can achieve temperatures of this order, that is, or of this low value, that is 4.2, by liquefying helium. Okay, it is very close to 0 Kelvin. Whereas hydrogen, boiling point of hydrogen, liquid hydrogen is 20 point something Kelvin. So, and helium is very costly. Why liquid helium is costly? Because इसको liquefy करना is a challenging thing. है ना? But we have to apply pressure, as I said earlier, that how we liquefy gases, उनको condense करना है. They are far apart from each other, so we have to condense them by applying pressure and decreasing temperature. So, so he used helium, Camberling Owens, and he used, because why he used mercury, pure mercury, क्योंकि मरकरी एक ऐसा मेटल है जो लिक्विड स्टेट में एग्जिस्ट करता है, ठीक है, और उसको हम लोग रिपीटेड डिस्टिलेशन से वी कैन मेक इट हाईली प्योर. Okay, so he selected mercury so that he can purify this by repeated distillation process, and he used helium because temperature of liquid helium is as low as this 4.22 Kelvin. So then he checked what is resistivity of this material at this temperature or lower than this temperature, and material is mercury, which is made highly pure. So this is the observation. Repeated experiments were done. Repeated resistivity measurements were done. And every time they observed that zero resistance is there in the material now at this temperature at 4.2. Okay, so they observed that resistivity of this mercury, it decreases with decrease in temperature, and suddenly at 4.2 Kelvin, resistivity becomes zero, no resistivity in the material. Okay, and when they were doing this experiment, during one repetition, experimental run में उनका जो technician था, who was performing this experiment for him, उसको नींद आ गया, he fall asleep, and जो प्रेशर उन्होंने जिसकी वजह से लिक्विफाई कर रखा था, तो प्रेशर एंड टेम्परेचर कंडीशन, प्रेशर रिलीज हो गया और जिसकी वजह से बॉइलिंग पॉइंट इंक्रीज हो गया, वो लिक्विड स्टेट से गैसियस स्टेट पे आ गया, एंड they observed that with this, when temperature goes above 4.2, suddenly resistance appeared. So this is reversible. If we increase temperature above this temperature is called critical temperature, where transition happens, where resistivity suddenly drops to zero. That temperature is what it is called critical temperature. For mercury, it is 4.2 Kelvin. Mercury undergoes transition from normal state to the superconducting state at 4.2 Kelvin. That's why for mercury it is 4.2. Okay, then after this, people started looking for other materials which can be made superconductors at low temperature. This was the first, that is, mercury was the first material which showed superconductivity, or which was tested for superconductivity, and it showed superconductivity at temperature 4.2 critical temperature. So it started with helium because helium was discovered, and then boiling point 4.2. So there is a coincidence that mercury का जो critical temperature for that was 4.2, and boiling point of this was also 4.2 decibel. So, statement was that mercury has passed into a new state. This is not that simply resistivity is zero, but it is a new state which is different from ordinary state. And this new state, it accounts for extraordinary electrical properties. And this state is named as superconducting state. Okay, so it is the phenomena, superconductivity is the phenomena where resistivity vanishes, and the state in when resistivity vanishes, that is called superconducting state. And this happens at a sharp temperature. This is not a gradual, this sudden change in resistivity from finite to zero. This happens at a sharp temperature, and that temperature where this transition happens is called critical temperature for the material. And critical temperature is different for different materials. So for mercury, it is 4.2. So Kamerlingh Onnes, he discovered superconductivity in 1911, and he was honored with Nobel Prize in 1913, 2 years after that. This is the actual graph showing how resistivity of mercury becomes zero. You can see it here. मेरा पेन नहीं चल रहा है आज ना इस पे. Okay, so this is how these are the measurements. You can see dots here. These are resistivity values. They measure at different temperatures. So at high temperatures, they measured that there is finite resistivity. Till here, it was finite. And after this, they saw that resistivity values, they dropped to very low values, or you can say approximately zero. How low it is? Below Tc, that is critical temperature for mercury, resistance was less than 10 raised to the power minus 23 ohm centimeter, that is 10 raised to the power 18 times smaller than for copper. So this is very low. So how we see that resistivity is zero, there's experiment for that. We have this mercury material, ring of mercury, you can say, hollow from inside, and it is at temperature 4.2 or less than that, means it is in superconducting state. And now if we apply magnetic field here, this is magnetic field. Due to change in magnetic field, we know EMF is produced, or you can say current is produced. It is as per so that then this current, if it remains there, because there is no resistivity in this material now, this is zero resistivity. So current will, because due to resistance and due to resistivity, as we saw that there is heating loss, or there is dissipation of energy. So there will be no dissipation of energy, and this current should continue in this loop forever if resistivity is zero. And this was done, these experiments and some theoretical predictions were done, and some calculations, some simulations, and they see their observations that current can flow for you can say 10,000 or more than that. It is 100,000 years. So there is a interesting paradox, and this is what materials which have high resistivity at room temperature, they are more likely that we can make them superconductors at low temperature. And whereas materials which have good, you can say good conductors at room temperature, they cannot be made superconductors at low temperatures. We'll see that when we'll do BCS theory. What is the reason? Because in in good materials, at room temperature, material is a good conductor. It depends when electron lattice interaction is minimum, or when charge carrier or electrons do not interact with the lattice, then that material is what that material is a good material, or that is a good conductor. But for a material to be superconductor, there should be strong lattice electron interaction. We'll see when we'll do BCS theory. So that's why there is this thing is observed that materials which are good conductors at room temperature, तो उनका lattice electron interaction कम होता है, इसलिए superconductivity they do not show. Then further discoveries were done. A race started to discover new materials, or not to discover superconductivity in new materials. Okay, so different materials were tried, different critical temperature. So there was a race that how to achieve critical temperature, high critical temperature, because it is difficult to maintain low temperatures or to go to low temperatures. So people started looking for materials which can be made superconductors at high temperatures. Okay, so during this time, that is from 1911 to 1986, low temperature superconductors were discovered, or you can say superconductivity was discovered. The highest critical temperature was 23 Kelvin for niobium germanium. ये जो मटेरियल है इसका टेम्परेचर क्रिटिकल टेम्परेचर 23, एंड मटेरियल्स व्हिच हैव क्रिटिकल टेम्परेचर लेस देन 23 they are put under this category, low temperature superconductors. ओके, देन एक ट्रांजिशन आया जहां पे इन 1886 हाई टेम्परेचर सुपरकंडक्टर्स, ये दिस इज पीपल स्टार्टेड वर्किंग अबव दिस, दैट इज 35 केल्विन. जो भी सुपरकंडक्टर जिनका क्रिटिकल टेम्परेचर इज अबव 35, they we put them under this category, that is high temperature superconductors. And this is lanthanum barium copper oxide. Okay, and this is a bad conductor at room temperature, but it can be made superconductor at this temperature, that is 35. And this was done by these two people, these two scientists, and they again they won this Nobel Prize in 1987 for this thing, that जो एक बैरियर था जहाँ पे 23 केल्विन से ज़्यादा कोई भी मटेरियल सुपर कंडक्टिविटी नहीं शो कर रहा था, टेम्परेचर मोर देन 23 केल्विन, तो वो बैरियर इन्होंने ब्रेक किया, एंड दे डिस्कवर्ड दिस न्यू material, synthesized this new material in lab, and this is their research paper showing that possible high TC superconductivity in barium lanthanum copper oxide system. And these are these two scientists, those who have published it in condensed matter physics. Then again this started, people started working on the same type of materials, and they achieved higher and higher critical temperatures. So immediately after this, in 1987, another material was tested for superconducting behavior, that was yttrium barium copper oxide, temperature 93 Kelvin, which is very much high than 35. These are high temperature superconductors now. Then again, this is bismuth, strontium, copper, calcium, copper oxide 110. Then titanium, barium, calcium, copper oxide, critical temperature 125 Kelvin. So this started then, people started looking for materials having more and more critical temperature, and you can see this is mercury, barium, calcium, copper oxide having critical temperature 133 Kelvin. So if we cool it down to 133, and 133 is not difficult to achieve, liquid hydrogen can do it, and it is also possible by other methods. So we can make superconductors at these high temperatures. These are high temperatures. Not high temperatures, we understand we are not talking about ordinary temperatures, but high temperatures in the sense where material can be made superconductor. So these are the materials, liquid hydrogen, nitrogen. This is liquid nitrogen, and liquid nitrogen. This is the barrier where you can see that this is helium having boiling point 4.2. So इससे low temperature पे superconductivity is not observed, but इसके बीच में liquid helium can be used, और यहाँ पे you can use what you can use, even liquid hydrogen. And we have effect of magnetic field on superconductivity. What affects superconducting state? Abhitar, we said that by varying temperature, we can vary resistivity, and by decreasing temperature, we can decrease resistivity. और एक ऐसा temperature जहाँ पे resistivity suddenly drops is called critical temperature. And again, if we increase temperature above this critical temperature, material again, resistivity again appears, and the material goes from superconducting state to the normal state. So means resistivity is depending on temperature. This was till now it was known that temperature is the only parameter or the factor which is affecting superconducting state. But it is not the only thing. It is with this there is another factor which affects the superconductivity of any material, and that is magnetic field. So if we apply magnetic field, we have a material which is in superconducting state, means temperature of the material is less than its critical temperature. Now, without varying temperature, without increasing temperature, it should remain in its state of superconductivity. But by applying magnetic field, by increasing magnetic field on this material, we can change state of the material from superconducting state to the normal state. So that means magnetic field, it destroys superconductivity. By increasing magnetic field, you have to take care of both temperature. You have to maintain material at very low temperature or below its critical temperature. At the same time, there is a magnetic field which is destroying superconductivity. Weak magnetic field, then we increase magnetic field, and there is a value where superconductivity will be destroyed, and that minimum magnetic field required to destroy the superconducting property of, of superconducting material at any temperature is called critical temperature. Okay, it is function of both. It is function of temperature. Sorry, not this. Superconducting state is function of both. It is function of temperature as well as function of magnetic field. So here we have plotted what we have plotted a graph, which is showing that we have taken both the variables, that is temperature as well as magnetic field at C, and we see that how material it goes from normal state to the superconducting state. And we see that this is the formula which gives you critical magnetic field, and critical magnetic field is also function of temperature. Okay, if I have a material or superconducting material which is maintained at temperature close to its critical temperature, then that superconducting state can be destroyed by applying small magnetic field. And if material is way below its critical temperature, then more magnetic field is required to destroy its superconducting state. And if material is at 0 Kelvin, then magnetic field required to destroy its superconducting state will be maximum. So it depends on both. Okay, material, critical temperature for any given superconducting material depends on material. What is the critical magnetic field required to destroy its superconductivity? Not only material, it also depends on temperature at which it is maintained. If, for example, I take mercury or I take any niobium, so you can see here, these are different. Critical magnetic field is different at fixed temperature, 0 Kelvin. So for different materials, at given temperature, for different materials, this Hc is what it is, different. So we are not seeing that dependence on material, but this relation is giving you what it is giving you. Dependence of this critical magnetic field for a given material. Material is given. For that given material, how it depends on temperature. So this is the relation. Hc is H naught. H naught here is what? It is the critical field at 0 Kelvin. If material is at 0 Kelvin, how much field is required? Magnetic field is required to destroy superconductivity or superconducting state. Times 1 minus T is the temperature at which material is, at which we want to know what magnetic field is required to destroy its superconducting state. and Tc is the critical temperature. So T is always less than Tc, only then we can say that material is in superconducting state. And square of this ratio T over Tc whole square. So this is what this is. This is plotted here. We'll see what this is. So let us try to understand if we have, if let me say that we have any material, superconducting material, and this is how it becomes superconductor at temperature. This is temperature axis, and this is resistivity axis, and this is the temperature, which is called critical temperature, where this transition happens. So if I keep this material at temperature equals to Tc, so it is at the verge of what? At the verge of this, that superconducting or this normal state. Okay, by applying now small magnetic field, we can destroy its superconducting state. But now if this material is, temperature of this material is very, very less than Tc, 4.2 Kelvin is required to make it superconducting, but we have kept it at 2 Kelvin temperature. So more effort, or you can say more magnetic field is required to destroy its superconductivity. Okay, and if it is at 0 Kelvin, so maximum is the maximum magnetic field is required to destroy its superconductivity, that is shown here. You can see that at material when it is at Tc, no magnetic field is required. You can say Hc for, or you can say Hc when T is 0, this is equals to H naught, maximum magnetic field. Okay, you can see when I put T equals to 0 in this expression, then this will be 0 and I will be left with 1 in the bracket, and that is H naught divided H naught times 1. So Hc is equal to H naught maximum. And when I put T equals to Tc, here I put T equals to Tc, Tc gets cancelled with Tc, I am left with 1 minus 1, that is 0. So Hc is 0. No magnetic field is required to destroy superconductivity at Tc. Okay, and if I go at, I maintain material at this temperature, then you can see according to this graph, this is the amount of magnetic field required to destroy its superconducting state. If material is at lower temperature, then higher magnetic field is required to destroy its superconducting state. Lower and lower is the temperature of the material, and higher is the magnetic field required to destroy its superconducting. So within this region, material is in superconducting state. And here you can say temperature is less than Tc. But if I go here, so then this is what this is more than the critical temperature. So material is in normal state. So this much field is enough to destroy its superconductivity. Okay, so this is important. Numerical point of view is important, and you should, for understanding of this critical magnetic field, you should understand what this relation is. Okay, and it is, as I said, that this critical magnetic field, it is material dependent. It is different for different materials, and with that it depends on temperature as well. So what is the temperature of the material that decides what is the critical magnetic field, what magnetic field should be applied to destroy superconducting state of the material. Then we have Meissner's effect. What this is, this Meissner, अभी तक race was only to discover superconductivity for different materials, or to increase critical temperature of superconductivity in different materials. Meissner studied effect of magnetic field on superconductors. Okay, and he discovered, or you can say he proposed another property of superconducting material. Till now, we said that superconductivity means resistivity is 0. If resistivity of any material is 0, then we say that okay, this is superconducting state and material is in its superconducting state. But Meissner said that it is not only rho 0 or resistivity 0 that decides that material is a superconductor or not. With this, there is another property, that is, if material is perfectly diamagnetic, susceptibility of material is -1. With this, that is rho 0, another property, that is susceptibility 1, qualifies material to be a superconducting material. Material is superconducting. If rho is 0, that does not mean that material is in superconducting state. That can be also said that it is pure conductor, highly pure conductor or conductor. There is no change in state. It does not go to superconducting state. So we'll talk about this more. I'll show it to you by 2, 3 experiments, and then we'll see what exactly Meissner's effect is. We'll also see video of Meissner's effect, which is very interesting effect, levitation of magnetic materials or above superconducting material. So application point of view से भी यहाँ से it starts application. अभी तक there was race only to see what materials are there which can be made superconductors and what are their critical temperatures. Then people started searching for materials having high critical temperature. So this happened till now. और इसके बाद application point of view से if this material is a superconductor, or then for what purpose or for what application it can be used, that starts from here. So with this, let us end today's lecture here only. If you have anything to ask, any queries, you stay back, you ask your queries, and the rest of you can hang up.